So as we've learned about different aromatic compounds, the presence of substituents will influence where new substituents go in any sort of electrophilic aromatic substitution reactions. Now, in this case, we have a group that we haven't seen before. And so we're trying to determine what it will do to the reaction as it takes place. But this group probably resembles a number of other groups that we have seen in the past. It looks somewhat like the sulfonyl SO3H group, and also looks a lot like the carboxylic acid group. And so we might expect that this group will behave in a very similar manner. And so with an aromatic question, it's never a bad idea if we don't know where to start drawing resonance structures. Because any resonance structures that we draw will help us to see where the electrons are. And so this phosphorus-oxygen double bond, just like a carbon-oxygen double bond, we can draw a resonance structure where the electrons move up onto the oxygen. That puts a positive charge next to the aromatic ring on the phosphorus, and so we can continue to draw resonance structures moving our electrons around. And what we see almost immediately from that second structure is we now have a positive charge at the ortho position. As we continue to move our electrons, we also end up with a positive charge at the para position. So if when we initially saw this structure we said that looks a lot like a carboxylic acid, we find that the behavior is actually identical to a carboxylic acid. And so by drawing the series of resonance structures, we can see that we have decreased electron density at both of the ortho and para positions. So we know this is a deactivating group, but more importantly, because of that, it will direct new substituents in any sort of substitution reaction to the meta to itself.